Okay, now let's relate our notion of linear independence to the idea of non-singular matrices. We know that non-singular matrices, when we use those to form a homogeneous system, then there's only the trivial solution. So it seems like there should be a close relationship between linear independence and non-singular matrices. All right, so let's see. Let's see. All right, so here we have two examples mentioned here. Okay, archetype A, if you go back and look at how this works, I guess we can go back there and see. Okay, these were the system. And it turns out that the coefficient matrix was singular. Since the coefficient matrix is singular, that means that there is non-trivial solution to the homogeneous system. So that means that the column vectors do give a linearly dependent set. Oops, that's not where I wanted to go. On the other hand, when I have a matrix whose columns are a matrix that's non-singular, then the homogeneous system has a unique solution, so the columns form a linearly independent set. So we summarize that in this theorem. Suppose that A is a square matrix, then A is non-singular if and only if the columns of A form a linearly independent set. All right, so this theorem pretty much formalizes what we've been talking about. So we can add to our list of equivalences for a non-singular matrix. Okay, we've already shown these other ones. If A is non-singular, if and only if it row reduces to the identity matrix, if and only if the null space contains only the zero vector, if and only if the linear system LS of AB has a unique solution for every possible choice of B, if and only if the columns of A form a linearly independent set. Okay. All right, well, let's go right on to this subsection. Okay, well, previously we showed that when we have a homogeneous system, let's do this here. When we have a homogeneous system, you could row reduce, and the solution could be expressed in terms of the non-pivot columns. Okay, so we express the solution to the homogeneous system as a linear combination of vectors derived from the non-pivot columns. But now we can ask the question, are these vectors linearly independent? Could I possibly, instead of, if I have three free variables, that is three non-pivot columns, is it possible that I could express my solution as a linear combination of only two of them? Do I really need all three of those column vectors? The answer turns out to be yes, and that's what we're going to talk about in this section. Okay, so in other words, there are no redundant vectors, there are no unnecessary vectors when we express the solution in terms of free variables. All right, so let's look at this particular example. There was a case where we had a matrix A which row reduces to this matrix here. Okay, so this is the coefficient matrix, and from this we can construct the solution to the homogeneous system. All right, and how do you do that? Well, you had free variables here, 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 and here. Okay. Now, these free variables meant we had four vectors. The four vectors had a structure that looked like this. Each of these four vectors had a 1 in the place corresponding to that free variable. Okay, for instance, for this vector here, the free variable is, I guess we're using we're using x1, x2. That's x3 is the free variable. Okay, so that meant that in this vector corresponding to this free variable, I'm going to have one entry corresponding to x1, another entry corresponding to x2, but I have a 1 corresponding to x3, and I have zeros corresponding to the other free variables. So this 1 corresponds to x3, this 0 corresponds to x4, another free variable, and I also have free variables x6 and x7. I have zeros for these also. Okay. Now my second vector that gives me, whose span gives me the solution set, I took 1 in the entry corresponding to the free variable x4. But the entry corresponding to all other free variables has to be 0. Same with this one. Free variable x6, 1 here, 0 for all the other free variables. The last one here, same here. Free variable x7, zeros in x6, x4, x3. Okay, so I can construct the null space as the span of 4 vectors, and these 4 vectors have this form. Okay, now the question is, are these vectors linearly independent? And that's the question. Are these vectors linearly independent? Well, look at the form of these vectors. These are entries I don't know what they are. These are entries I don't know what they are. These I don't know what they are. These I don't know what they are. This I don't know what it is. Okay. So the question is, are these 4 vectors linearly independent? Now, turns out that they are. And the way you can see that is, suppose we took this matrix comprised of these 4 vectors and tried to row reduce. Now the way we can row reduce is we can simply exchange the rows. We would take this row, move it up to the top, take this row, move it to the 2nd place, this row, move it to the 3rd place, this row, move it to the 4th place. Then we would end up with 1, 1, 1, 1, zeros here, zeros here, and then there would be some other junk down here. But the other junk down here doesn't matter, because I can use these vectors here to eliminate. I can use this first vector to eliminate the first column. I can use this vector to eliminate the 2nd column. I can use this vector to eliminate the 3rd column. I can use this vector to eliminate the 4th column. So the row reduced form of this set of vectors is going to be the identity matrix stacked on top of several 0 rows. No free variables. That means that these column vectors are linearly independent. Okay? All right, so that's kind of the way that he's going through here. Okay. And the formal statement of what I just said is here. Let me go through this again. A lot of this is restatement. He's just adding one more condition, which is here. Suppose I have a m by n matrix, and B is row equivalent in reduced row echelon form. R pivot columns, just as before, and these are the pivot indices, and F non-pivot columns, and these are the indices. Okay. Now, because I'm not considering the inhomogeneous system, I don't have n plus 1 columns. I only have n columns. You can consider there's an imaginary n plus first column that has all zeros that doesn't come into the argument. Okay. Now, from this reduced row echelon form, I can construct these vectors. These are the same vectors that I had previously in my theorem before. You can look back and see this. This theorem here, SSNS. Look back there and see that these are the very same vectors. Okay. Now, first I know that the null space is the span of these vectors. I proved that previously. The new thing is that this set is a linearly independent set. Okay. Now, he goes through the linear independence here. This is formal proof, but the idea of the proof is, as I mentioned, when you construct these vectors, it always has this form. The vectors have this form. When I row reduce the matrix consisting of these columns, then I'm going to get the identity matrix stacked on top of a set of 0 rows. That means that the matrix has n pivot columns, means there's no free variables, means that there's no non-trivial linear dependence relation. There's no non-trivial linear dependence relation. Okay, there's another example, and that does it for this section.